In this video I'm going to be talking about the basics of trigonometry, so sine, cos and tan, how you can use them to find angles and lengths in a right angle triangle using trigonometry, so using SOHCAHTOA. There are a lot more things you can do with sine, cos and tan, like trigonometric identities, sine and cosine rule. That is all covered in my other videos. This video is a basic introduction, so what sine, cos and tan actually mean and how we can use them. So if we start by looking at this right angle triangle, we have been given that one of the angles is 30 degrees. That means we actually know the third angle as well. Because it is right angle, we know that we have an angle of 90 degrees, an angle of 30, so our other angle must be 60 to get the 180 degrees that we need in a triangle. If we then have a look at another triangle that has a 90 degrees angle in it, so a right angle in it, and again we are told that one of the angles is 30, we know that this is just an enlargement of our previous triangle, because again that angle must still be 60. So it is exactly the same triangle, just made bigger. That means that if the upright side is twice as large, we've gone from 5 to 10, then our diagonal side must be twice as large as well. So this side must be 20. If we have a look at another right angle triangle, again with an angle of 30 degrees in it, but this time we are told that the diagonal length is 2. This time it has got 5 times smaller than our original, which means that our upright must be 5 times smaller or must be equal to 1. If we think about each triangle individually then, we can see that our upright side here, 5, is half of our diagonal 10. And again in our larger triangle, the 10 is half of our diagonal 20. And in our smallest triangle, the 1 is half of our diagonal 2. This is very important because in all three of these triangles, the side that is opposite to our 30 degree angle is always half of the side that is opposite the right angle. So you might have done some work on triangles and know that we have special names for the three sides. The longest side, the one that is opposite the right angle will always be the longest, is called the hypotenuse. So in all three of these cases, the orange side is the hypotenuse, and the green side has the very sensible name opposite, because it is opposite the angle that we know, the 30 degrees in all of these cases. The other side, just for information, which we will be talking about later, is called the adjacent, because it is adjacent to or next to the angle that we are talking about. So we've got a hypotenuse, an opposite and an adjacent. And in the case of 30 degrees, so when our angle is 30 degrees, we know that the opposite is always equal to half of the hypotenuse. So I'm going to use a capital O for opposite and a capital H for hypotenuse. So the opposite is always half of the hypotenuse, and we can rearrange this to a ratio that the opposite compared to the hypotenuse, or opposite over hypotenuse, is equal to a half. That is only when the angle is 30 degrees. Because it is right angles, we know one of the angles is 30 degrees, we know all three angles, so we have fully defined the triangle. In that case, the side opposite the 30 degrees is always half of the length of the side opposite the 90 degrees. This is what trigonometry is based on. It is purely a ratio of the length of the sides. So I've just done 3 quick triangles and they are all in slightly different orientations, and we're thinking about different angles. So in this case we are thinking about the angle down here, which means that this is the side that is opposite to it. The hypotenuse is always opposite the right angle, that's always the longest side. However, the opposite and adjacent sides depend on which angle you are thinking about. So in this bottom left triangle, although it is exactly the same as the top one, we are now thinking about the angle up here, which means that the side on the bottom here is the one opposite. So the opposite and adjacent have switched around because we are thinking about the different angle. In the case on the bottom right here, the angle has been rotated around, but the right angle is here. So we know that this is the hypotenuse. This is the longest side. It's not always obvious by first looking which one is longer, but you know by the fact that it is opposite the right angle. We are then thinking about this angle, so our one opposite that is the one over here, which leaves our adjacent to be this side. So it's important you know how to label the three sides of a triangle to be able to use trigonometry correctly. So if we drew out a triangle, a right angle triangle with 30 degrees, and make the hypotenuse have a length of 1, from what we looked at before, the opposite was always half of the hypotenuse when we had 30 degrees. So we know that this side would be equal to a half of 1, which is 0.5, or a half. If we then measured the length adjacent to the 30 degrees, we would find that it had a length of 0.866. So that would always happen. If you don't believe me, you can draw it out and draw a right angle triangle with 30 degrees, make the hypotenuse 1 and measure the other two sides. But what is important is it doesn't actually matter how big we make it. If instead we had drawn it with a hypotenuse of 2, the opposite side would always be half of that, so in this case would have been 1. And the adjacent side would have been 0.866 of that, so would have been equal to 1.732. So this is very important for trigonometry because it's the ratio of the sides stay the same. If we have a right angle triangle with 30 degrees in it, we know that the opposite side is always going to be half of the hypotenuse. So we can record that. If we've got an angle theta of 30 degrees, I use the Greek letter theta here because it is often used as angles, but you might see it as x or a for angle. But if we have an angle theta of 30 degrees, we know that the ratio of the opposite to the hypotenuse is equal to 0.5 because the opposite is always half of the hypotenuse when the angle that we're talking about, or the angle inside the right angle triangle, is 30 degrees. Equally, we can look at the ratio of the adjacent to the hypotenuse, in this case 0.866. The adjacent will always be 0.866 times the hypotenuse. There is one other ratio we can do. We've compared the opposite to the hypotenuse, the adjacent and the hypotenuse, so the other ratio is the opposite and the adjacent. And if you do the opposite divided by the adjacent, you will find that the opposite is 0.577 times the adjacent, or lots of the adjacent. So this here actually gives us the ratios of any right angle triangle that has 30 degrees in it, so the ratios of the sides. So that can be very, very useful if you know that you have a right angle triangle with 30 degrees in it and you know one of the sides, you could work out the length of the other sides because the ratios will be what we've written down here. Now we could do the same thing with a different right angle triangle. As long as it's got a right angle and you know one of the angles, you know what the other angle will be as well. And in this case, if we make the hypotenuse equal to 1 and then measured the opposite side, we would find that it is 0.707. And again, the adjacent side, because it's 45 degrees, it's actually isosceles, so they would be the same, 0.707. Again, it doesn't matter how big we had made it. If instead we had made this length equal to 2, then the opposite side would be 0.707 times 2, which is 1.414 long, and the adjacent would be the same as the opposite, 1.414. So we've already listed our ratios for 30 degrees. Now if instead of a 30 degrees angle we had a 45 degrees angle, the ratio of the opposite compared to the hypotenuse is 0.707 if the angle is 45 degrees. The adjacent compared to the hypotenuse is the same as the opposite compared to the hypotenuse, 0.707, but the ratio of the opposite compared to the adjacent is actually 1. They are equal. The opposite is 1 times the adjacent. So we've now listed out the ratios for 45 degrees. So if we had a 45 degrees right angle triangle, we could work out 2 of the other sides if we knew one of them by using this set of ratios. We could then go through and do the same thing for all the triangles ranging from 1 degrees up to 89 degrees, or even more than that. We'd have to do the point degrees, so we'd have to do 0.1 degrees, 0.2 degrees, go even smaller than that. There are an infinite number of triangles we can draw by making the increments in angles smaller and smaller. Luckily, this has already been done for us and been tabulated. So here you can see that if we know the degrees in our triangle, so if we drew a triangle that had about 15 degrees in it here, we could look up 15 degrees and this would tell us the ratio of our sides. Our opposite would be 0.2588 times our hypotenuse, Our adjacent would be 0.9659 times our hypotenuse, and our opposite would be 0.2679 of our adjacent, which makes sense because the opposite side here is actually a lot smaller than the adjacent or the hypotenuse, but the adjacent and the hypotenuse are not that different in length. So this is just a table of all the angles that increment in 1 degree this time, so all the different angles you could have in a right angle triangle, and it tells you the ratios of the sides. So this is where sine, cos and tan come from, because sine of the angle is known as the ratio of the opposite to the hypotenuse. Cos of the angle is the ratio of adjacent to hypotenuse, and tan of the angle is the opposite compared to the adjacent. Now sin is actually short for sine, it's the sine of the angle. Cos is short for cosine, you might have heard of that, it is the cosine of the angle, and tan is just short for the word tangent. So sine, cosine and tangent are the full words, and sin, cos and tan are the shortened versions that are used in equations, but they are exactly the same thing, just a long way or short way of saying it or writing it down. But all sin theta is, or sine of the angle theta is the ratio of the opposite compared to the hypotenuse. So in our example we looked at earlier, we can say that sine of 30 degrees is equal to a half or 0.5, because we know that the opposite was always half of the hypotenuse, so the ratio of the opposite to the hypotenuse was a half. And if you look down here in our table, that fits here. 30 degrees has an opposite compared to a hypotenuse of 0.5. So sine 30 degrees just means the ratio of the opposite to the hypotenuse when we have 30 degrees in our right angled triangle. Now that's important because I've often seen people write in an equation sin on its own. That doesn't make any sense. You can't just have sin. That would be every set of values in this table for the O over H. That would be a little bit like writing a square root sign in an equation without having the square root of something, which wouldn't make sense. You can't have, for example, 3 times the square root equals x, because you'd be thinking, well, the square root of what? It's the same thing. Sine is like an operation. It has to be the sine of something. So you can't just have sin written on its own in an equation. You have to have an angle. It could be sin of any angle, but you have to have an angle. So sin 19, for example, would mean that you are looking at this bit on the table, so sin 19 would be 0.3256. So sin 19 is 0.3256, which actually tells us if we drew out a right angle triangle with 19 degrees in it here, if our hypotenuse was 1, then we know that the opposite would be 0.3256. So for the ratios, we could actually look up the values in tables if the angle is exact to a degree. So if we wanted 1.5 degree, we might have to interpolate or estimate. But luckily, you don't even have to look the values up in a table. Your calculator stores all that information for you. So SOHCAHTOA is the acronym used to help remember which one is which. So you split it into 3 parts, your SOH, CAH and TOA. And it just helps you remember which one is which. Some people write it like this to help them remember which bit goes on the top, but it is just in the order of how you would say it. So the SOH part of it tells us that the sine of the angle, and remember again, we have to have an angle there, you can't just have sine on its own, but the sine of the angle is equal to the ratio of the opposite side compared to the hypotenuse. So SOH, S-O-H, tells you the first 3 letters in your equation, and it is a whole equation. It tells you CAH tells you that the cos of the angle is equal to the adjacent over the hypotenuse. So again, CAH, C-A-H, the first 3 letters in your equation, and you've probably guessed, but the tan of the angle is equal to the opposite over the adjacent, and that is given to us by the TOA in TOA. So all SOHCAHTOA is it is reminding you which ratio each of the sine, cos and tan are referring to. I've known a lot of people who use their calculators for sine, cos and tan without really understanding what they're doing, and they just fiddle around with the numbers until they get an answer that looks sensible. It helps if you understand what your calculator is doing, and all it is doing is telling you the ratio. So we've said that the sine of the angle is just the ratio of the opposite compared to the hypotenuse. So if you type into your calculator sine 30, all it is effectively doing is looking up a value in this table. So sine of 30 is down here, and we already knew it from earlier, is 0.5. So if you type in sine 30, your calculator will give you 0.5. Equally, if we type in cos 59, that is just telling you the ratio of the adjacent compared to the hypotenuse when the angle is 59. So it is looking up in this table for an angle of 59 what the cosine of it is. So in here, 0.5150. So type into your calculator cos 59 and you will get an answer of 0.515. Equally, tan, if I typed in, for example, tan 20, that is just looking up the tangent of the angle 20 degrees, so it would give you this answer here, 0.3640. So all your calculator is doing is effectively looking up the values in these tables. So it is not doing anything magical, it is just giving you the ratio of the sides, and depending whether you type in sine, cos or tan, depends on which two sides it is giving you the ratio between. And this is simply what we are doing when we use sine, cos and tan to work out the lengths of a triangle where we know the angle, or to go the other way and tell us what the angle would be if we knew what the ratio was. So if we knew that the opposite was half of the hypotenuse, we could look up a half here and that would tell us the angle of 30. We will look at how to do that using your calculators later, but for now let's have a look at some examples of how to find the lengths using trigonometry. So let's have a look at a question where we are given the angle of a right angle triangle and one of the sides, and we need to find the other two sides. So how can we use SOHCAHTOA to find this? So I would start by writing SOHCAHTOA if you aren't used to it and can't remember your three ratios, and labelling the three sides of your triangle. So the 3.5 centimetres is the side that is adjacent to our angle, so that is the adjacent. The hypotenuse is always the longest side opposite the right angle, and the opposite is the side that is opposite the angle that we know, but obviously not the right angle. So to find x, we are trying to find the opposite, and we know the adjacent. So we've got our O and our A. So if we look at the SOHCAHTOA, it is actually the TOA that we need. Both SOH and CAH have H in it, and we don't yet know our hypotenuse. So we are going to be using TOA, which remember tells us the whole equation. It tells us that the tan of the angle is equal to the opposite over the adjacent. So then we can fill in the information that we know. So our angle is 34, so the tan of 34 is equal to our opposite x over our adjacent 3.5. So we can rearrange this to get x on its own by multiplying both sides by 3.5. So x is actually equal to 3.5 times the tan of 34. We could look up 34 in our table and find out what that is, but you have a button on your calculator to do that, so you can type it in exactly as it's written here. So type in 3.5 times tan 34, and that will tell you that x is equal to, and when you type that in, you will get 2.36. So if you looked up tan 34 in the table, that was 0.6745. Or if you typed in tan 34 into your calculator, that is 0.6745. Either way, you get the same thing from the table or the calculator. Multiply it by 3.5 and you get 2.36. To find the length of side y, that is our hypotenuse. So we have h. We now have found out what the opposite is, so we do know our O and our A. However, we've calculated O and you might have made a mistake there. So it is always better to use the one that was given to you in the question. So in this case we are using A. So we are looking for the part of SOHCAHTOA that has A and H in it. So in this case it is CAH. So I am going to use CAH, and I've rewritten it because it doesn't go HA, it goes AH, and that tells me my whole formula, which is cos theta equals the adjacent over the hypotenuse. Again, we fill in the parts that we know from our triangle, so cos 34 is equal to our adjacent 3.5 divided by our hypotenuse, which is what we're trying to find, y. Now you need to do a bit of rearranging to find y. So we multiply both sides by y to get y times cos 34 equals 35, and then we divide by the cos 34. So 3.5 divided by cos 34. Type that into your calculator and it will give you an answer of 4.22, and it is centimetres. We were given units in the question, so our answer should have units, and equally we should have put the units of centimetres on our answer for x up here. So check that your answer of 4.22 is sensible. We are finding the length of the hypotenuse, which is always the longest side. So you are expecting an answer bigger than 3.5 but not ridiculous. So if you had accidentally done it the wrong way round and times by cos 34 instead of dividing by cos 34, your answer would have come out smaller than 3.5 and you would have known you were wrong. So just sense check your answers to make sure that you are getting it correct. So now we've done an example, pause the video and have a go at these two questions. So for this first question, we are looking at 27 degrees. I'm going to start by writing out SOHCAHTOA, just to remind me which ratio I need to use, and then labelling the sides. So the 5 centimetres is the hypotenuse, the x is my adjacent, and the y is my opposite. So to find x, that is my adjacent, I know adjacent, and I also know my hypotenuse 5. So I'm looking for the part of SOHCAHTOA that has the adjacent and the hypotenuse in it, that is the cos or the ca. So that tells me my whole equation, which is that cos of the angle, remember cos has to have an angle, is equal to the adjacent over the hypotenuse. So fill in the parts you know. Cos of 27 is equal to the adjacent x divided by the hypotenuse 5. Multiply both sides by 5 to tell you that x is 5 times cos 27. Type that into your calculator and you will get 4.455 centimetres. So to find y, this time I have my opposite, and again I'm going to use the hypotenuse because although I could use the adjacent x, I've actually worked out that value. So it's best to use the value that you've been given in case you made a mistake in your calculations. So this time I've got the opposite and the hypotenuse, which means that I need to use the SO part of SOHCAHTOA. So SO gives me my equation, which is that the sine of the angle, which is equal to the opposite over the hypotenuse. So fill in the parts that you know. We know the angle, so sine 27 equals y over 5, and rearrange that by multiplying both sides by 5, and that will give you y is equal to 5 times sine 27. Type that into your calculator and you will get 2.270 centimetres to 3 significant figures. Question 2. My triangle is not the same way up as my previous triangle, but my right angle is this angle at the top, which means that y is my hypotenuse. That means that 4 is the one opposite the 62 degrees that I've been given, and the x is the one adjacent to the 62 degrees. So first of all, to find x, which is my adjacent, I've also been given the opposite. So I'm going to be using the opposite and adjacent in my calculations, which means I need the O and the A in TOA. So this time it tells me that tan theta is equal to the opposite over the adjacent. So if we fill in the parts we know, we've got tan 62 is equal to the opposite 4 over the adjacent x. Now x is at the bottom of the fraction here, so to find it we need to multiply by x to give us x times tan 62 and then divide by tan 62. So the x and the tan 62 effectively switch places. Type that into your calculator and you will get 2.127, and again that is centimetres. So it's always worth sense checking your answer. So does that make sense in terms of what we have in our original triangle? You might look at that and think, actually, no, it doesn't make sense because x clearly looks longer than the opposite, which is 4 centimetres, so we should be getting an answer bigger than 4. However, if you have a look at the angle 62, this diagram is clearly not drawn to scale. That angle is definitely not 62. It looks somewhere more in the region of between 20 and 30. So don't get thrown off by your diagram. Just check that your answer is sensible, and check that if you know your hypotenuse must be longer than the other two. So 2.127 does make sense. So now we need to find y. Y is our hypotenuse, and again I'm going to use the opposite rather than the adjacent because I was given the opposite. So I need O and H, which again is going to be the sine. So sine theta is opposite over hypotenuse. Fill in the parts you know. Sine 62 is equal to 4 over y, and again we do the same things, multiply the y up and then divide by the sine 62. So y is 4 over sine 62, which when you type it into your calculator gives you 4.530 centimetres. So again, sense check it, it is longer than the other two, so that answer does make sense. So we've looked at how we can use trigonometry to find an unknown length in a right angled triangle, but what if we don't know the angle, but we do know two of the sides? If I start by labelling the sides that I know, this one is my hypotenuse because it's the longest side opposite the right angle, and this one is my opposite because it's opposite the angle that I need to find. I can see that I've got opposite and hypotenuse. So if I again write out my SOHCAHTOA, we can see that we are going to need the SOH part. So again, remember that just tells us what equation we can use, which is that sine theta equals opposite over hypotenuse. So this time, if we fill in what we know, we don't know the angle, so that can just stay as sine theta, but we do know both the opposite and the hypotenuse. So sine theta is 1 over 2 or 0.5. Now if you think about what that means that we actually know the ratio of the opposite to hypotenuse and we need to get back to the angle. So if you think about that in terms of our sine tables, where this is the sine column, if we look down for 0.5, that tells us that the angle we're looking for is 30 degrees. We already know what the sine of the angle is and we need to get back to the angle. So effectively we're going the other way in the table. Instead of knowing the angle and looking up the ratio, we know the ratio and we're looking up the angle. How do we use our calculators to find that? What a lot of people do here is they would start with the sine theta equals 0.5 and they think, I want to get theta on its own. Normally two things next to each other in algebra mean we've times, so I'm going to divide by sine, and they write something that looks like this. But if you remember what we talked about earlier, this makes no sense. You can't just have sin on its own. It has to be sin angle or sine of an angle. If we just have sin, that effectively means the whole column in this table, this whole column. And obviously that isn't just one number, that doesn't give us an answer. To get an answer we need sine of an angle, so you cannot just do this. So what can we do? What we have is this function on our calculator called inverse sine, and it looks like that, sine to the power minus 1 it looks like, but it doesn't mean to the power minus 1, it means the inverse sine function. So it means that you know what the sine is and you want to get back to the angle. So you do the inverse sine of 0.5. So you get rid of the sine on the left hand side to leave the theta on its own by doing the inverse sine, which gets rid of it from the left hand side and makes it appear here on the right hand side. So if you type into your calculator sin minus 1 or inverse sine of 0.5, it will give you your answer, which is 30 degrees. If you can't find that button on your calculator, it is normally achieved by pressing shift and then the sign. If you look above your calculator, there will be a little sign to the -1 above your sign button. So that just means the inverse function to sine. So you can never get rid of a sin or a cos or a tan by dividing by it because it has to have an angle. but you can do an inverse sine function, which means you are going the other way in the table and trying to find the angle if you already know what the ratio is or what the sine is. So let's have a go at another example. Let's start by labelling the two sides that we know, and in this case the 5 is opposite the angle that we're trying to find, and the 3 is adjacent to the angle that we're trying to find. So if we go back to our SOHCAHTOA to remind us what our equations are, we need the O and the A for opposite and adjacent, so we're going to be using TOA. That tells us what our equation is going to be. That is tan theta is equal to the opposite over the adjacent, and then we can fill in the parts that we know. We don't know the angle, but we do know that the opposite is 5 and the adjacent is 3. You could put that into your calculator and work it out, but that will give you a recurring decimal, so it is easier just to leave it as a fraction. So this equation tells us what tan of the angle is, but we want to know the actual angle, so we need to get rid of the tan. So remember, to get rid of a sine or cos or tan, you inverse it, which means that we inverse tan the other side, and it is written as tan minus 1, and to get that on your calculator you do shift tan. So tan minus 1 of 5 over 3, type that into your calculator, and that'll give you 59.0 degrees. So hopefully you're seeing it's not too difficult. You just must remember that you cannot just divide by tan to leave the theta on its own, because you can't have a tan without an angle. What you have to do is inverse tan it, and the inverse tan is written as a tan minus 1. So to check your understanding, pause the video and have a go at these two questions. So question number 1, if I label the sides that I know, the 4 is the hypotenuse because it's opposite the right angle, and then the 2 is adjacent to the angle that I'm trying to find. So if I write out my SOHCAHTOA, in this case I need the one that has A and H in it for adjacent and hypotenuse, so that is going to be the CA part of SOHCAHTOA. So this tells us that the equation we're going to use is cos theta equals the adjacent over the hypotenuse. So if we fill in the parts we know, we don't know the angle, but we know that the adjacent is 2 and the hypotenuse is 4. So we get cos theta equals 2 over 4, or that does simplify down to 0.5. We want the theta on its own, so we need to inverse cos it. So cos to the minus 1, 0.5, and type that into your calculator, gives you 60 degrees. Question 2 then, this time 7 is the hypotenuse and 5 is actually opposite to the angle that we're trying to find, so I need the part of SOHCAHTOA with O and H in it, which is SO. So that tells us to use the equation sine theta equals opposite over hypotenuse. So sine of theta, which is what we're trying to find, is equal to the opposite 5 over the hypotenuse 7. This again doesn't give you a nice finite decimal, so leave it as a fraction. To get the theta on its own, we need to inverse sine both sides, which gives us sine minus 1, 5 over 7. You can type that into your calculator, and it gives you 45.6 degrees. So I hope that that has helped you to understand the basics of trigonometry. You must remember that trigonometry only applies to right-angled triangles. You cannot use these rules if it is not right angle, because it is the ratio of the sides when you know that one of the angles is 90 and you know or are trying to find another angle in the triangle, and because all three angles add up to 180, that fully defines the triangle. If you don't know that it's the 90 degrees angle, you don't have enough information, so you can't use trigonometry for any triangles unless you know for sure that it is right angled. You also, a key mistake that people make is when they want to get rid of a sin or a cos or a tan, they try and divide by it, but remember it has to be sin angle, cos angle or tan angle. You can't have a sin, cos or tan on its own, so to get rid of it we do the inverse function, which is written like this with a minus 1. That doesn't mean to the power minus 1, that means the inverse cos function. As a quick reminder, try and remember when you are finding a length you know the angle, so you will just be using sin, cos or tan. When you are finding an angle you don't yet know the angle, so you need to inverse sin, inverse cos or inverse tan it. So hopefully that has helped, and I will see you again soon.